So, yeah, here's gonna be your problem for today.
All right, Daryl. Um, so the question I'm going to give you today is a tree question, and it's going to focus on tree traversal.
Mm,
Um, the question is called "Count good nodes in a binary tree."
mm,
And so the way it's going to work is I'm going to have you, so that you're going to be given the root of a tree, and you're going to count how many nodes qualify as good. And the way a node qualifies as good is when on the way to that node, there are no nodes that are bigger than that value.
okay, okay. Wait, are you typing right now? You're not, right?
No, not right now.
Okay, okay. So the definition of if it's good, if if you're traveling down the tree. Wait, sorry, say it again.
Yeah, so let me actually just copy in the text here.
Okay.
1 second. There you go.
Oh, okay, okay, great. Hmm. Okay, so given a binary tree root, node X in the tree is good if the path from root to X, there are no nodes with a value greater than X. Oh, okay, so then you return the number of good nodes in the binary tree.
Yeah, so let me just give you an example here. So we might have a tree like that where it's 3, 1, 3 on one side, and then on the next side we have 4, 1, and then 5. So
Mm.
here, the nodes that are good are does the structure of this kind of make sense?
Yeah, it makes
Kind of
sense. Yeah.
half-ass the drawing, but
Mm.
so here the nodes that count as good would be, well, 3, because the path to 3 from the root is 3, and there are no nodes bigger than it
Mm.
in that path. 1 is not good because 3 is in the path and it's bigger, right?
Yeah.
And then 4 is good,
Mm.
and then 5 is good.
Mm.
Yeah.
Okay.
So you want to, so the input is going to be some root,
Mm.
and then the output is going to be 4 in this example.
Okay. Hmm. Okay. Okay. That makes sense. Yeah. Okay.
Yep. So that's the question.
Okay. So I'm just thinking of this through my head. We're gonna have to be able to traverse the tree in some way, and with the tree, with each value in the tree, we're gonna want to have to keep track of what all of the parents are. So my initial thought of what we can do right now is we can do a basically a depth first search, and with that depth first search, we can basically add. Okay, so basically we have to add every single value onto like a queue, right? Or I guess like a stack. Yeah, let's say a stack. And with the stack, we can pretty much just pop each element, checking to see like what its children is, and then adding it to there. So okay, let me just kind of flesh out this idea by going through the example with it. So
Yeah, sure.
okay, so we're at 3 right now, and then we add 3 to like a hypothetical stack over here, and with that, we pop 3 from the stack and we add its children. So 1 and 4. With 1 and 4, we like um we we know that in order for the children to be a good node, it has to be um it has to be basically greater or equal to 3, right? So we have to have a check in that sort of way. um so given the stack, basically check to see if children are greater than I guess the parents, right? And then from
Yep.
there we have to add that children's children to the stack if they exist, and from there we have to keep track to see whether or not that's greater than the parents, well, greater than the current one we're on, for so in this example one. And we also have to simultaneously check to see whether or not it's greater than 3 as well. So
Hmm.
in order to do that, one idea, so I'll just like kind of go through this and see like whether or not it's worth pursuing. But um we can have like a tuple. So like in the stack, for example, we have 3,
Hmm.
and then we have and basically maybe let's say like a set of values which are like the parents pretty much, right?
Hmm.
So we have 3, and 3 doesn't have any parents, so we leave that. um we pop and we check these children, and then we have 1. We add 3 to that set before checking that one's children again.
Hmm.
Also, okay, so from there, we check to see, let's see, like 3, and this time we can have it passed in as a parameter where we add like every single item in this existing um like hash set over here and add it to here, and then we also add like the parent, which is 1 over here.
Hmm.
So
Right.
basically, like once we get to 3, we'll reach the stage, and then from here, we'll have this. We'll check to see for the definition of a good node, which is whether or not like it's greater than. In this case, it is because it's a greater or equal to, and then from there we can return we can add that to basically like a result variable, um like a result variable at the very end that kind of like adds it up. So yeah,
Right.
so and then like we can basically like keep continuing this process with like every single value, basically keeping track of the parents this way. Is this is this something like a valid solution?
Yeah, so the traversal sounds good. I think although there is a more memory efficient way for us to you know that second item in the tuple.
Mm-hmm. Oh, like a hash
So the
set,
second
yeah.
item in the tuple, yeah. So the second item in the tuple is you're basically storing the whole path towards the node
Right.
that is the first item in the tuple, right?
Yeah.
Uh, but like given the context of the question of what we're trying to check, I feel like we don't need to actually store the whole path.
Right. Okay. So, hmm. Okay, maybe instead of like storing this like every like the whole path in for like every individual one, what if we have
Mhm.
like another basically like in another array instead, like having visited. So like we add
Mhm.
for 3, we can add that, and then we'll add 1, and then um so on and so forth. uh oh yeah, 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 like that, would that be that would be more memory efficient. I guess because like the space complexity of this worst case should be like visiting like the height of the tree. So like the space complexity of that would be o of h, right? Would that be something better? Or-
Uh, I think so. I think the main thing is we actually don't need to know the whole path if to check whether a certain like say we're at a certain node and we want to see if it's a good node. We
Mm,
don't actually need to know the whole path up to that node. We can make do with just one other piece of information.
right, right. Okay, so
So yeah.
okay.
So say you're at that node
Mm,
and you want to check if it's um say you're at that node and you want to check if it's a good node. And we did go with your initial implementation. What would you do?
so okay, so we made so you said it, basically you're saying we make it to here, and then we're going by original implementation. I checked to see like whether or not all of them. I checked to see whether like that value, the first value, is matching with any of the ones that like have been visited, right?
Right. So you're saying, so like, let's say you go with your initial implementation and we're at that like three on the left, right?
Yeah,
Um, so when we pop from the stack, we would have the number three and then the path set, which contains one and three, right?
yeah.
What do you do to check that three is a good node given that information?
you check to see whether or not it's like a greater than 3 and 1. Oh,
Right.
maybe okay, okay, is what you're like okay, an idea would be maybe to have some sort of comparison like for 3 and 1 first before you do the comparison. So instead of keeping track of everything, you keep track of the largest. So
Right. Right. Yeah, exactly.
so maybe like we can stick with that tuple idea, but instead of having like basically like a hash set, we have just like the largest value, right?
Yeah. Yeah, exactly.
Okay, so does this sound like a solution I can begin coding up now?
Yeah, that sounds great to me. You might want to did you want to try like polishing up that example first though, just so uh
Right. Okay, so I can run through this example with it then. Okay, let me start over here. Okay, so basically we start off at 3, and from there we add um okay, wait, let me like do like a stack. Um, basically we add 3 to the stack, and then we get like what like it's kind of like the maximum it has, which basically it's like nothing. So we'll just set that to like let's say like 0, right? And then
mhm.
with this value, we pretty much just pop this item from the stack, and um, okay, so we pop that item and we add its children to the stack first. So from there, we add 1 and what is it? Yeah, yeah, like we add 1. Um, okay, okay, wait, 1, and then we add like the maximum value, which is from there, which is 3. While we pop it, we actually we when we pop it is when we can actually perform the operation to check to see whether or not it's a good node. So like maybe we can
Mhm.
have like a node for that too. Uh, when pop check for node. Basically check if good node, and then from there, then right. Okay, let me just think. Yeah, so from there, then we can add like 1 and 3, and then we can like like rinse it and repeat that kind of operation all the way until the very end. So
Mhm.
yeah, and after that, we can have a result, which is equal to 0, and then if good node, then increment res, right? So
Yeah.
yeah, okay, so and then we keep going on up until we have a guard that checks to see like whether or not like the current node in the iteration like well, I guess like we check to see like whether or not the stack is empty, and then
Mhm.
like once the stack is empty, like that's when the program will end, will return the result. Is that good?
Yeah. Yeah,
Okay,
that sounds good. Do you want to try coding it up?
okay, sounds good. So yeah, first things first, we're gonna have like the maybe like define like good nodes, and then we're given the roots. So from here, first thing we can do is have results, set it equal to 0, and then we're gonna want to end up returning that. Next thing we do is we have the basically the stack, and then we okay yeah okay so we have the stack, and then we add root, and then 0 0 initially, and then
Mhm.
while the stack exists, we're
Oh,
gonna
do you want to just fix that indentation real quick?
oh what the heck sorry,
Uh,
a trip out
yeah.
okay well, I don't know where that
Yeah,
came
all
from.
good. All
Okay,
good.
um okay, so while the stack exists, that's when we're gonna want to
Mhm.
add the children. So first we want to have the guard to check to see whether or not oh you have to pop it. So um cur equals stack dot pop um oh yeah,
Mhm.
so we add the current and then max. So we pop those two values out of the stack, so there'll be root and 0, and then we want to check if not cur, then that's when we're gonna want to return. Actually, yeah, actually, if not occur. Oh, okay. If cur, then we need to perform the following, right? So, okay, yeah. Um, if the current value exists, that's when you want to add. Well, I guess like we have to add the cur dots or stack. Um, we want to append the left one stack and the right one, And in
Mhm.
order to do that, we also have to figure out what the maximum is. Now, this is where we have to do some thinking over here. So, okay, we have the cur and we have the max. Set the pop. We want to check to see like if oh, actually, we can just reset this over here. Max equals like I guess like, oh, whoops, I forgot. Max is a keyword in Python actually, so it might error out if we use that as a variable name.
Mhm. Good catch.
We'll try a max and get the maximum of the current max and the cur, and then if okay, so we grab that and then we add like the maxi to the left and the right, and then here is where we're actually yeah, here's where we're actually gonna do the check to see. So if let's see, the definition of a good node is no nodes with a value greater than x. So if the current value is like a greater, yeah, actually greater or equal to the current maxi, that's when we're gonna want to append, or I guess increment the res. So uh right, okay, let me just think about that. Yeah, yeah. So this is the res plus equal to 1. We're
Mhm.
gonna want to add those values, and then that's when we're gonna want to append the cur to the left, cur dot right, um, and yeah. So you'll be popping through every single element in the stack until it's all over, and then from there on, that's when you're and yeah, you'll just be adding that, getting the maximums. Sorry, and yeah, that should be good. Let me just go ahead and run through an example just to make sure like I'm getting the null values correctly with our current example. So
Yeah, for sure.
let's say we okay, so we have 313. Um let's say like the stack in that position. Well, actually, we'll do this. Add this over here. Okay, so we add 3 and 0, and then we add 1 and 3. Okay,
Hmm.
so we're here. Okay, basically, okay, let's start here. We're at the root, and then we pop this. So this is popped out already. It disappears. And we know what the maximum is now. The maximum is 3 in the curve, which is 3. So we check to see, um, like is the curve greater or equal to the maxi? It is because it's greater than 0. So res is equal to 1 now. Now the next thing we do is we append the left. So that would be 1, and then we add uh, 1 and 3, and then we also add uh, 4 and 3, and then yeah, okay, we keep on going going on so forth. Let's say for the sake of this example, we'll go for 1 and 3. Um, for this one, when it loops through again, it checks this, like it does it for each of its children, right? Because it checks it in the stack
Hmm.
eventually, and this check, if it's cur, will prevent it having. Ooh, actually, hmm. This maxi needs to. The maximum actually needs to belong. Actually, I don't think it matters either way because. Wait. Yeah, Oh, wait a minute. We need to check the code.val. Uh.
Yeah,
Sorry.
good catch.
Yeah. I just realized because, yeah, you can't compare with the actual object itself. It has to be the value. And then
Right,
also,
right.
positioning of the maxi. I have to think about this one too. If cur doesn't exist, then this may produce a null pointer exception. So this check has to be done over here.
Yep, also good catch.
Yeah. If no cur exists, then all of this will be skipped, and yeah, basically, okay, yeah, it shouldn't. Yeah, it shouldn't affect anything, and like all of this will finish, and it'll just move on, and I guess like pop the next item, in the stack.
Yeah,
Okay,
yeah.
yep, that's my final solution. Time complexity of this one would be let's see, I gotta think about this. So time complexity, traversing through every single element, O O of n, and the space complexity of this one will also be O of n because in the worst case you could have everything in the, well, I guess Yeah. Actually, yeah. Yeah. Space complexity of this would be O of n, because worst case you could have everything like evaluating the tree in the stack. Yeah.
Hmm. Okay, that's correct. That's the right solution.
Is it?
Um,
Okay.
yeah, it is, bro.
What the heck? Okay, yeah, sorry.
That interview was actually really good. So I think a couple things I want to note out is one is it was good that it was very good that you like started off by kind of like examining the example that you had.
Uh-huh.
You almost tripped up by coming up with the idea on how to solve it before examining the solution.
Uh-huh.
Sorry, the example. Because something I noticed is like something that almost happened was you almost looked at the example with a biased view on what your solution is,
Oh,
and you
right.
started looking for like whether your preemptive solution would work or not, instead of like just trying to find out details in the example.
Right.
Um, but you got out of it and you like went in the right direction.
Mm-hmm.
So that was good. Like so, looking at that example in the beginning was very good. The
Mm-hmm.
other thing I noticed that you did that was different from your previous interview was you asked about the high level if it was good first before coding it up.
Oh, yeah,
Um,
yeah. I think you'd waste them last time.
yeah,
Yeah.
yeah. So you saved yourself. Well, I mean, you had it right in the beginning, but like if it were wrong, you would have saved yourself a lot of time by
Mm-hmm.
asking that question.
Mm-hmm.
Um, let's see. I mean, like your depth first reversal iteratively. That's pretty fire.
Uh-huh.
Let's see what else. Uh, I think this is like is pretty minor.
Mm-hmm.
But you see how here you basically you like even if the next even if the left child is null, you put it in the stack anyways, right? And then on the
Oh,
next
right.
iteration, you let the while loop handle it.
Yeah.
Um, so the thing is like you would end up with like children in the stack that are null anyways and like and that are null and are going to get rejected anyways, right?
Right.
So it's better if you don't add them in the first place so that you don't use up that extra like computer time rejecting it.
Oh, so
And
maybe like if
yeah,
not cur, then you do like return, like nothing, right? Wait, no, not
or more
return.
so
Wait.
like
Or, I don't know. I forgot. Yeah. Yeah. Go on.
it's a I think you're looking for continue, but like what I was referring to, what I would suggest is
Uh-huh.
actually you would do if cur dot left then append.
Oh, I see.
Yeah. Also, did you know Python can do like one line if statements? I don't know.
No idea. I didn't know that was a thing.
Yeah.
That's
So
crazy. Yeah.
if cur dot left append and if cur dot right do that. And
Mm-hmm.
now that you know that the stack will never pop a null node, you don't have to worry about like stuff like maxi not being able to evaluate because cur dot val is invalid.
Oh, yeah. Right. Right. That makes sense. Yeah.
Yeah.
Oh.
Um. Yeah. So like going through that example is good. I think like honestly, one like decent example of going through it is enough to catch most things.
Uh-huh.
But I think you would have caught something else if you look through like a simpler example or like a few more examples.
Right.
Uh, because there's actually a edge case that you're not handling right now in the code.
Oh, wait. What is it?
It's I can't I what if I let you handle it? You know,
Oh, okay. Right now. Oh, okay. Okay.
pl
Okay. Let
play a
me think.
little
Let me think. Let
play
me
a little
think.
hard to get.
Okay. Okay. Sounds good. Hmm. Okay. So smaller example. Let's say like Okay. We have. Okay. We can. So let's go with like 3, 1, and 4. Um. Actually, to make it more edge casey. Actually, yeah. 3, 1.
Uh, hmm. Maybe I should give you a hint. What if I have negative values? Specifically, what if the root is like -10? What happens? Try running it.
Oh, if the root's -10. Oh, this should be Is this what you're referring
Yeah,
to? Oh,
yeah, that's
right.
exactly right.
Yeah. Wait,
So
what? Oh, sorry. My bad. Ugh, I think I messed up. I should have asked for the constraint like earlier on the problem. Yeah.
Honestly, if I that might be on me because it's not too crazy an assumption given the fact that I didn't give you a constraint.
Uh-huh.
Yeah, but it's like it's very minor, and I'm sure like the in the in an actual example, the interviewer would know to actually give you the constraint. But yeah,
Mhm.
like you got it, man. Like that was a fire interview.
Oh, thank you, dude. It's better than like my first couple. I got yeah. Okay, it's good to see that I'm actually improving a little bit. Yeah.
Yeah, yeah. I think like intermediate step that might flesh out your interview a bit more
Mhm.
is before you code it up, putting it in pseudocode.
Okay,
Um,
pseudocode,
I
right?
think I think once you have like a solid idea of the high level, it's not too crazy an idea to go straight into code, but I think it would be better if you went for pseudocode, which you kind of did, like informally with the when pop check if good node that thing.
Oh yeah, right.
But
It's better
um,
to like Python is out kind of like a little bit, right? Yeah.
yeah, actually, like keeping this comment was a very good idea, I think, even if you were to go forward with pseudocode. But after
Hmm.
writing this comment, I would go through and try out pseudocode.
Oh, okay, okay, right. Hmm.
Yeah, unless actually maybe not. Never mind. I feel like the solution is simple enough that I would just go straight for code.
Yeah.
Never mind.
I think for
Yeah,
like
that was a
yeah,
mhm.
maybe for like this kind of problem, it's like okay, but like if it was like doing like trapping rainwater or something like along your line, it would have been a lot better to do pseudo. Yeah, I know
Yeah,
what you mean.
maybe if the solution was like complex, yeah, start with pseudocode. Like I don't know. I think my monkey brain wouldn't be able to handle it personally.
Mm. Okay, that makes sense. Yeah. Okay, I'll keep that in mind.
Yeah.
So okay, so for next time, um, have like smaller like simple examples, ask for constraints, and then uh the little stack issue, and then yeah, okay, that makes sense. That makes sense. Okay, thanks. Yeah.
Yeah, but like, but the feedback that's generic, like, sorry, the general feedback that goes for um interview best practices instead of like feedback that's specific to this question
Mhm.
is, I think, when you're doing traversal, don't add null nodes to the stack.
Right, right. Don't add null
Yeah,
nodes to stack.
and
Right. Yeah.
yeah, and then in the beginning, ask clarifying questions. Like, not every question will require that you do, but
Uh-huh.
yeah, ask clarifying questions. And one last thing, I think there's one last um, small comment that I had that I completely forgot.
Mhm.
Let's see. What was it? It's um, oh, don't use arrays for your stack. Use deck. Use the because the problem is when you use an array to
Oh.
implement a stack or queue in Python, it like um, inserts are oven operations, I think. Yeah, so you definitely want to use deck. But
Oh. Oh, so like
that's
this one, right? Wait,
yeah,
I
yeah.
thought a deck was a double-ended queue.
Yeah, yeah, yeah. So you can use it also. You can use it also as a
Oh,
stack.
and to use it as oh, because you can just call the pop function, right? The pop function works regardless, right?
Yeah. So like you pop for. So basically, you like append the same way, either like stack or queue.
Yeah.
But you use dot pop for stack,
Mm.
and then you use dot pop left for queue, because you're like popping where the
Right.
linked list implemented, like, because it's implemented as a linked list, and if you use
Right.
dot pop, you're just popping the like the head node, which would
Yeah.
give you a stack like behavior. But if
Yeah.
you do pop left, then you're popping from the left of the array, or not the array, the linked list. So that would
Right.
give you queue like behavior.
Right. Right. That makes sense. Yeah. Yeah. Okay. Like that's
Yeah.
yeah. I wish I knew more Python, bro. Yeah.
No, no, that's all good, bro. Like this is a simple like Google search, just like syntax for deck, and you're
Yeah.
good.
Oh, this brings me to like another question I had. This is like related to this at all. Do you think it'd be more beneficial to do these kind of problems in C++? Like probably not, right? Because like they have like
Uh, I
standard uh data structures.
I I don't think so. I think like, because you would interview in Python, you should just aim to be as familiar as possible in doing leak code in Python.
Oh, okay, okay, right. That makes sense. Yeah, yeah. And I was
Yeah.
also thinking for like for like the Microsoft when they give me like the problem, like I think Bo's kind of surprised I asked to do it in Python. I think that's just like an interview quick thing, right? Not like a
Oh,
general
really?
like because he originally he wrote
Damn,
the
that's
problem
sus.
statement and stuff in like C++, and he's like, "Can you code it in C++?" And then I had to go like actually go and ask him, "Would it be possible to do it in Python instead?" And then he asked why, and then I
Can
said
you
because I lead code, and then like yeah,
can you code in C++? No.
yeah,
um,
yeah.
um,
Maybe it's just like an interview quirk. There's some like
yeah, like that's kind of weird. Maybe it's just because like the job is C++ heavy, but
right, right.
um, like unless that's the case, it's really weird that an interviewer would not be okay with or like would like be
Yeah.
adamant on a language.
Yeah, I don't think I was just like a low level programmer in the first place, which is maybe why he was more familiar with it. But yeah,
I see. I see.
yeah.
Okay, well, I mean that's everything I have to say about the interview. That was good, Matt. Good job. Five.
Okay, thank you, thank you. Yeah. Okay.